Usually when we talk about like a medical diagnosis,
Hmm.
there's this expectation of precision. It almost feels, I don't know, engineering adjacent.
Right. Yeah. Like it should be exact.
Exactly. Like you break your arm, the X-ray shows that jagged white line right on the radius bone, and the doctor just points at the illuminated screen and says, "There it is. That is the point of failure."
Yeah, it's a binary state.
Right.
It's either broken or not broken. You can literally trace the physical disruption. And, there's a comfort in that. We inherently like things to be visible, to be categorized, and to have a single isolated root cause.
But then, you step into other fields, say, like the world of neurodevelopment or complex autoimmune diseases, and suddenly that X-ray machine is just useless.
Completely useless.
We're looking at a diagnostic landscape that is, honestly, it's incredibly murky. Like symptoms overlap, systems influence other systems totally invisibly, and the root cause might be, 3 layers deep.
It is the absolute definition of diagnostic muddy waters. And frankly, that is the exact same transition an engineer makes when they move from troubleshooting a single physical server in a closet to diagnosing a distributed auto-scaling microservices architecture in the cloud.
You completely lose the X-ray machine.
You do. You lose it entirely.
Well, welcome to a very special edition of the Deep Dive. Today, we're shifting into high gear. We are putting on our hats as cloud architects for a highly targeted session.
Oh, yeah.
We are setting our sights on the AWS Certified DevOps Engineer professional exam, which is, widely known as the DOP-C02.
The dreaded, highly respected, and incredibly dense DevOps professional.
It's a beast.
It really is. I mean, if you are listening to this, you are probably prepping for a massive infrastructure migration, or you're catching up on the field of cloud deployment, or, you are just insanely curious about how massive global distributed cloud systems actually hold together under immense pressure.
And our mission today is highly specific. We've gathered a massive stack of material. We're talking raw scenarios, community discussion threads, and just intense public forum debates.
There are so many debates out there.
So many. But our goal is not to just read you a list of correct architectural decisions so you can, memorize them.
No, please don't do that.
Right, because memorization might get you a piece of paper, but it will absolutely cause you to take down a production environment on Black Friday.
Oh, 100%.
We want to help you internalize the deep underlying systems engineering. Why? Why does one specific architecture hum along flawlessly while another, seemingly identical architecture just collapses into a pile of timeout errors under a sudden traffic spike?
Because knowledge is most valuable when it's understood mechanically, and applied practically. There is always, always more to learn about the physics of the cloud.
Yeah.
And passing any kind of technical evaluation, it should merely be a byproduct of actually comprehending how these AWS services physically interact behind the curtain.
And here is the core issue we've identified across all these public study forums. We call them the hive mind traps.
So the hive mind traps are dangerous.
They really are. You scroll through these discussion boards, and people are upvoting answers based entirely on, buzzword association.
Yep.
They see the word lambda and the word latency in a scenario, and they immediately just aggressively advocate for whatever architectural option includes the word concurrency.
Or they see a deployment failure and vote for the option that involves the absolute most complicated scripting.
Exactly. It is a dangerous, superficial game.
Yeah.
And it leads to fundamental anti-patterns in live production environments. So we are going to deconstruct these scenarios, tear apart the bad advice to see why it's so tempting, and reveal the optimal AWS well-architected solutions.
Because critical thinking is essential in a world of information overload, especially, when that information is crowdsourced engineering advice. That sounds highly plausible, but completely ignores the underlying physics of a database engine.
Okay, let's unpack this. Let's jump right into a classic architectural bottleneck. This is perhaps the most common friction point in modern cloud environments. What happens when highly elastic, infinitely scalable serverless compute slams headfirst into the very rigid physical constraints of a traditional relational database?
It's a classic clash of paradigms.
It really is.
Yeah.
So imagine this setup. A company recently deployed a web application on AWS, and they're gearing up for a massive, heavily marketed, large-scale sales event. Traffic is expected to go from baseline to stratospheric in seconds.
Okay.
The architecture looks incredibly solid on paper, The front end is an Amazon CloudFront distribution sitting in front of an Amazon S3 bucket as the origin.
Which, by the way, is the gold standard for highly scalable static asset delivery.
Right.
CloudFront caches the HTML, CSS, and JavaScript at the edge locations globally. I mean, it can handle almost any volume of traffic you throw at it without breaking a sweat. It just absorbs that initial impact of the user influx.
But the back end is where things get tense. The back-end infrastructure relies on an Amazon API Gateway REST API. That API routes incoming dynamic requests to several AWS Lambda functions.
Okay, standard serverless pattern.
Yep. Those functions contain the business logic, and they ultimately connect to an Amazon Aurora database cluster to read and write the transaction data.
Okay, I see where this is going.
So the DevOps team conducts a rigorous load test to simulate the upcoming sale event. The good news: the Lambda functions scale beautifully and handle the peak number of concurrent requests.
Nice.
The bad news: the engineering team notices massive request latency during the initial burst of the load test.
Uh-oh.
The system crawls to a halt for a few minutes, they dig into the traces, and here is the smoking gun. Most of the requests require database queries, and a shockingly large portion of the Lambda invocation time is being spent just establishing the network connections to the Aurora database.
Yeah, that's the killer right there.
So I'm looking at the forum debates on architectures like this, and the hive mind trap is just so predictable. People see latency and Lambda, and they immediately suggest configuring a higher reserve concurrency or a higher provision concurrency for the Lambda functions.
Of course they do.
It makes sense on a superficial level, right?
Yeah.
If your workers are slow, add more workers.
It seems intuitive, sure, until you look at what a database connection actually requires at the microscopic level. You have to understand the TCP handshake, the TLS encryption negotiation, and the actual database connection protocol.
Right, it's not magic.
Exactly. Every time a new Lambda execution environment spins up to handle a concurrent request, it is an isolated, secure micro-virtual machine. It initializes its code, loads its libraries, and then it has to reach out over the network to Aurora to establish a brand new database connection.
Which takes time.
Establishing a connection to a relational database is computationally brutal. It requires network back and forth, authentication validation, and crucially, allocating dedicated memory and a specific process thread on the database instance itself.
So it's not just sending a quick ping or a stateless UDP packet.
No, not at all.
It's like a heavy formal introduction. The Lambda function is essentially saying, hello, I am Lambda environment number 4392. Here are my encrypted credentials. Please validate them, negotiate a cipher suite, and set up a dedicated stateful communication channel just for me.
And that takes time, and more importantly, CPU cycles on the database. Now imagine a sales event where traffic spikes from 0 to 10,000 requests per second almost instantly.
Oh boy.
API Gateway scales effortlessly. It just passes the traffic. Lambda scales horizontally, spinning up 10,000 completely independent, concurrent execution environments in a matter of seconds. And all 10,000 of those isolated environments simultaneously turn around and aggressively knock on Aurora's door, asking for a heavy stateful connection setup.
It's basically a distributed denial of service attack coming from inside the house.
Yes.
Aurora just falls over under the weight of the handshakes,
Yeah.
not even the actual database queries.
Right. It experiences what we term connection thrashing, which leads to complete connection starvation. Aurora instances, being relational databases, have hard limits on the maximum number of concurrent connections they can support.
Because it's tied to RAM, right?
Exactly. This limit is physically tied to their RAM. So if you throw more Lambda concurrency at this, which is what the forums often suggest, you are actually weaponizing the compute layer against your database.
Wow.
You are intentionally increasing the size of the mob banging on the database's front door. You guarantee that even more Lambda functions will try to open even more connections simultaneously. The database spends 100% of its CPU just rejecting or queuing connection attempts and 0 CPU executing actual SQL queries.
That toll booth analogy really works well here. You have a massive 10-lane highway of traffic coming in, that's Lambda. But they all have to funnel through a single-lane toll booth where they have to stop, roll down the window, hand over a physical toll card, and wait for a receipt that's the Aurora connection handshake.
That's a perfect analogy.
If you just widen the highway to 20 lanes, you haven't solved the bottleneck. You've just created a wider traffic jam at the toll booth.
Yep.
So provision concurrency might solve a Lambda compute cold start, but in this specific architecture, it absolutely ruins the database. We need a buffer. We need something to absorb the shockwave.
And this is where we introduce the systems level fix, which is Amazon RDS proxy. The architectural mandate here is to create an RDS proxy for the Aurora database and update the Lambda functions to use the proxy endpoint instead of the direct database endpoint.
Okay, so break down the physical mechanics of RDS proxy for me. Like, how does sitting a proxy in the middle magically fix the database's memory limit?
So RDS proxy is a fully managed, highly available database proxy service. It sits architecturally directly between your highly elastic Lambda fleet and your rigid Aurora database. Instead of each Lambda function attempting to open a dedicated, heavy connection to Aurora, the Lambda function connects to the RDS proxy. And here is the secret sauce. The proxy maintains a relatively small, persistent, established pool of connections to the backend database.
So the proxy does all the heavy handshaking with Aurora in advance, like during quiet times.
Precisely. The proxy opens a manageable pool, let's say 500 connections. It does the TCP handshake, the TLS negotiation, the authentication. Those 500 connections are now wide open and waiting.
I see.
When the sales event hits and those 10,000 Lambda functions spin up, they don't hit Aurora, they hit the RDS proxy. And connecting to the proxy is incredibly fast. The proxy then multiplexes it, intelligently shares and borrows those 10,000 incoming Lambda requests across its pool of 500 already established database connections.
So the Aurora database only ever sees 500 connections.
Exactly.
It stays completely happy.
Yeah.
Its CPU isn't tied up doing thousands of handshakes per second. It just receives a steady stream of SQL queries flowing through those 500 wide-open pipes.
Yes. The proxy absorbs the connection storm. If 10,000 requests come in and the 500 connections are currently executing queries, the proxy will simply queue the incoming Lambda requests for a few milliseconds until a connection in the pool frees up. It completely shields the database from the brutal, instant horizontal scaling of the serverless compute layer.
That is amazing.
This is why understanding the mechanics is non-negotiable. You have to internalize that Lambda and Aurora scale on fundamentally different paradigms. Lambda scales by multiplying. Aurora scales by growing larger. You cannot directly couple a multiplying layer to a static layer without a shock absorber.
That is incredibly clear. You just can't scale the compute if the data layer requires persistent stateful connections.
Sure.
Okay, let's stay in this serverless neighborhood, but let's pivot slightly to a different type of latency friction.
Sure.
We just talked about network and database bottleneck latency. But what about when the compute itself is the slow part? So imagine this scenario. We have an application relying on an Amazon API gateway invoking a Lambda function. Simple enough. However, on initialization, the code inside this Lambda function is written to load a massive payload of reference data from an Amazon DynamoDB table.
Okay.
This data load process is resulting in brutal, unacceptable latency. We're talking cold start times of 8 to 10 seconds before the function can even process the user's request.
That's practically an eternity in serverless time.
Right. Now here is the twist. The engineering team already put a cache in place. The DynamoDB table has DynamoDB Accelerator, commonly known as DAX, configured and running. Yet customers are still complaining about intermittent slow responses.
Interesting.
The traffic pattern is also highly specific. They get a steady baseline of thousands of requests, but right in the middle of the day, traffic spikes 10x. Then near the end of the day, it drops off a cliff down to 10% of normal volume. The mandate is to reduce the latency of the Lambda function at all times of the day, consistently.
Okay, I know exactly what people on the forum say about this.
Right, my instinct here, and what I see echoed in a lot of community discussions, is deeply confused. People suggest deleting the DAX cluster and just setting a provision concurrency of 1.
Yeah, that's the hive mind trap.
Let me walk through my confusion out loud. DAX is an in-memory cache. It sits in front of DynamoDB specifically to deliver data in microseconds instead of milliseconds.
Yep.
So if DAX is sitting right there and the query is cached, why on earth is it taking 8 full seconds to return a payload? That physically doesn't make sense to me. Why would anyone suggest deleting a cache to speed things up?
Your confusion is entirely justified, and it points to a fundamental industry misunderstanding of what a cold start actually is in the context of AWS Lambda. People conflate data caching with compute initialization.
Oh, I see.
They assume that if data retrieval is fast, the whole function is fast. But that's not true.
Okay, separate those two concepts for me.
All right, a cold start occurs when AWS needs to spin up a brand new secure execution environment, a firecracker micro VM for your Lambda function. This happens because there aren't any idle environments available to handle an influx of new concurrent requests.
Nice. Yeah.
During this cold start, there is a distinct multi-step phase called the init phase. AWS has to allocate the underlying infrastructure, launch the micro VM, bootstrap the runtime, whether that's Node.js, Python, or Java, download your actual deployment package from internal S3 storage, and then execute the initialization code outside of your main event handler.
Right. The global scope.
Exactly.
And in this specific scenario, during that global init phase, the developer's code is explicitly instructed to go out over the network, grab a massive chunk of data from DynamoDB, and load it into the Flux's local memory footprint.
Exactly. Now, bring DAX back into the picture. DAX is a data cache. DAX is doing its job perfectly. It is responding to the read request in microseconds. The network call to fetch the data is incredibly fast. But the Lambda function itself still needs physical time to spin up the execution environment, bootstrap the runtime, make the API call to DAX, receive that massive multi-megabyte payload of data over the network, and computationally allocate it into the runtime's memory space before it can even begin to serve the user's actual API requests.
So DAX is handing the data over instantly, but the sheer volume of data being moved into the Lambda environment's memory, combined with the container spin-up time, is taking 8 seconds.
Precisely.
The network cache cannot fix the local compute initialization overhead. It's like having a lightning-fast delivery driver drop a massive pile of IKEA furniture at your door. The delivery was fast, but you still have to spend hours assembling it in your living room before you can sit down.
That is a phenomenal way to visualize it. If you delete DAX, which is the hive mind suggestion, you are going to make the data retrieval slower, compounding the problem. And setting provision concurrency to a static value of 1 doesn't help at all when traffic spikes 10x in the middle of the day. You'll just have one single warm instance, and the thousands of other incoming concurrent requests will all hit cold starts, spin up new micro VMs, and spend 8 seconds building IKEA furniture.
Which leads us to the actual elegant system architecture. The solution here requires keeping DAX, but dealing with the compute initialization explicitly.
Yes.
We need to configure provisioned concurrency on the Lambda function, but not statically. We need to configure AWS application auto-scaling on the Lambda function with provisioned concurrency values set to dynamically scale between a minimum of 1 and a maximum of 100.
This is the correct multi-layered approach. Provision concurrency, unlike standard on-demand concurrency, tells the AWS control plane to completely pre-initialize a specific number of execution environments. It intentionally runs that 8-second init phase before a user request ever arrives.
So AWS spins up the container, runs the global code, makes the ultra-fast call to DAX, downloads the massive data payload, allocates it into local memory, and then the container just sits there, fully loaded, idling.
Yes. The environments are pre-warmed. When the user request finally hits API gateway and is routed to Lambda, the function doesn't need to initialize. It is immediately ready to execute the handler code against the data already in local memory.
Wow.
The 8 to 10 second cold start latency is completely eliminated from the user's perspective. They experience millisecond response times.
But why introduce the application auto-scaling component? If provision concurrency solves the problem, why not just set it to 100 manually and walk away?
Because of the financial physics of the cloud.
The bill.
Always the bill. The traffic pattern explicitly states that demand drops to 10% at night. Provision concurrency is not free. You pay a premium for AWS to keep those environments pre-initialized and sitting idle in memory. If you set a static value of 100, you are burning your budget all night long for 90 idle containers that are doing absolutely nothing. That makes total sense.
By integrating AWS application auto-scaling, you can create a scaling policy, either a target tracking policy based on utilization metrics, or a scheduled policy based on known traffic patterns.
So knowing the traffic spikes midday, application auto-scaling can gradually spin up the provision concurrency to 100 pre-warmed environments right before the rush hour.
Exactly.
Then, as traffic dies down in the evening, it automatically scales that pre-warmed pool down to 1.
Exactly. You maintain DAX for the microsecond data retrieval from the database layer, and you use dynamically scaled provisioned concurrency to eliminate the compute initialization tax at the application layer.
Yeah.
It is a perfect, cost-optimized synthesis of compute scaling and data caching.
That is incredibly satisfying when you break it down mechanically. It's not just about knowing what the services are. It's about tracing the life cycle of a request and knowing exactly where the friction happens, whether it's network, memory, or compute.
You have to follow the packet. Always. Okay, let's transition our thinking. We've fixed the runtime scaling, We've got our serverless compute and our databases living in harmony. The application runs flawlessly.
Right.
But a running application is only half the battle. How do we safely deploy changes, updates, and new features to these environments without breaking them?
The deployment pipeline.
Yes, this moves us into the labyrinth of CI/CD, continuous integration and continuous deployment. Let's analyze a scenario I like to call the phantom instances.
Ooh, spooky.
It really is. This involves the intersection of AWS CodeDeploy and EC2 autoscaling. Here is the setup. A DevOps engineer is using AWS CodeDeploy to push a new application revision across a fleet of Amazon EC2 instances.
Okay.
These instances are running inside an EC2 autoscaling group to handle dynamic load. The deployment group in CodeDeploy is configured to perform an in-place deployment using the CodeDeploy default one-at-a-time configuration.
Right, very standard.
The deployment kicks off, the engineer monitors the console, the progress bar moves, and eventually CodeDeploy proudly reports that the overall deployment finished successfully. Green check marks across the board.
Awesome. Time to go home.
You would think. But when the engineer SSHs into the actual servers to verify, they discover a nightmare. 2 out of the 5 instances currently running in the autoscaling group have the old previous application revision deployed, and only 3 have the new version. The fleet is mixed.
Oh, that is a nightmare.
This is baffling. If I run a deployment script and the orchestrator tells me success, I expect success. I'm looking at the forums and people inevitably assume a script failed.
Yeah, they do.
They suggest that an after-install lifecycle hook failed on those 2 specific instances, rolling back the code deploy agent to the previous version, but somehow leaving the overall deployment status as successful.
It's a very common assumption because developers are used to scripts failing. But if we analyze how CodeDeploy actually reports status, that theory falls apart immediately. If a lifecycle hook script, like an after-install script, fails on an instance, CodeDeploy explicitly flags that specific instance deployment as failed. Furthermore, depending on your rollback configuration, it would likely halt the entire pipeline or trigger an automatic rollback.
Right.
It would absolutely not silently report a clean, overall successful deployment while deliberately leaving instances in a failed rolled back state. The orchestrator is designed to bubble up failures, not hide them.
So if CodeDeploy didn't fail, what's the actual mechanical failure here? Why do we have old code on new servers?
To find the root cause, we have to look at the interaction between the deployment orchestrator and the infrastructure orchestrator.
CodeDeploy and autoscaling.
Exactly. You have to visualize how autoscaling and CodeDeploy interact during an active deployment window. When CodeDeploy starts an in-place deployment, it doesn't continuously monitor the fleet. It queries the autoscaling group at the exact moment the deployment begins and takes a static snapshot of the current running instances.
Okay, a snapshot.
Let's say at that moment, the ASG has 3 instances running. CodeDeploy builds a checklist of those 3 specific instance IDs. It begins deploying to them one at a time because the configuration is CodeDeployDefault.18 This is a slow, methodical process.
Okay, I have a checklist of 3 servers. I start updating server number 1.
Right. Now, what happens if, during the slow 20-minute one-at-a-time deployment, the website suddenly gets a burst of traffic? The CPU utilization across the instances spikes.
Oh, I see.
The autoscaling group's CloudWatch alarms trigger, and the ASG decides it needs to scale out to maintain performance.
The ASG kicks into gear. It looks at its configuration, specifically its launch template or launch configuration, which points to a specific Amazon machine image, an AMI.
Exactly. And here is the fatal flaw, that AMI is the base image. It contains the old version of the application code because the new deployment hasn't finished baking a new AMI yet. So the ASG launches 2 brand new instances using that old AMI.
But wait, doesn't CodeDeploy intercept new instances? I thought there was an integration where CodeDeploy automatically pushes the latest code to any new server that spins up.
There is an integration, and it relies on autoscaling lifecycle hooks. Normally, when an ASG launches a new instance, the lifecycle hook pauses the launch, CodeDeploy intercepts it, deploys the last successful revision to the new instance, and then lets it enter service. Normally. However, during an active deployment, the definition of last successful revision is tricky, and race conditions occur. Code deploy is laser-focused on finishing its active batch based on its original snapshot.
Right.
Depending on the exact millisecond timing of the scale-out event relative to the deployment phases, those new instances might boot up with the old AMI, and code deploy essentially misses them in the context of the new revision rollout because they weren't on the original snapshot checklist.
Yep.
By the time the two new instances fully join the fleet and signal the load balancer that they are healthy and ready for traffic, code deploy finishes updating the original 3 servers, checks off its list, and correctly declares that it successfully deployed to the 3 instances it knew about.
Wow. It's literally like hiring a painter to paint a moving train.
Yes.
He looks at the train, counts 3 unpainted train cars, and starts painting. Meanwhile, the train conductor hooks up 2 more unpainted cars to the back of the train. The painter finishes his 3 cars, clocks out, and says, "I successfully painted the train."
Mm-hmm.
And you look at it and see 2 completely unpainted cars at the end.
That is brilliant.
So the ASG scaled out from 3 to 5 instances right in the middle of the deployment. Code deploy updated the original 3, the ASG added 2 with the old code, and you end up with a fundamentally broken, mixed fleet, even though every tool technically did exactly what it was told to do.
Precisely. This highlights why in-place deployments on actively scaling dynamic groups are inherently risky. You are creating a race condition between the deployment agent trying to mutate the state and the scaling policies trying to expand the state.
So if in-place deployments are playing Russian roulette with auto-scaling, how do you avoid this? What is the enterprise standard?
This exact race condition is why blue-green deployments were invented.
Yeah.
Instead of mutating a live, breathing scaling fleet, you leave the current production environment, the blue environment, completely alone. You provision an entirely new auto-scaling group, the green environment. You deploy the new code to the green environment while it's receiving 0 public traffic. You ensure it's stable, and only then do you shift the load balancer traffic over from blue to green.
Which perfectly transitions us to the next architectural scenario, which is entirely focused on blue-green deployments and the absolute dark arts of code deploy app spec lifecycle hooks.
Oh, the app spec file, everyone's favorite.
Let's analyze these requirements. A company is automating their software deployment pipeline. The business requirements are incredibly strict, as they should be, for a mission-critical app.
Go for it.
Requirement 1. A specific number of instances must be available to serve traffic during the deployment. Traffic must be balanced, and instances must auto-heal if they fail.
Okay.
Requirement 2. A new slate of instances must be launched automatically, with absolutely 0 manual provisioning by the engineering team.
Got it.
Requirement 3. Traffic must be rerouted to the new environment slowly, specifically, to half of the instances at a time. The deployment must automatically fail and roll back if it cannot route to at least half.
Makes sense.
Requirement 4. Before routing any live user traffic to the new fleet, temporary files generated during the deployment compilation process must be completely deleted from the disks.
Ooh, tricky.
Requirement 5. At the end of a successful deployment, the original instances must be deleted immediately to save on compute costs.
This is a textbook, highly resilient, enterprise-grade deployment pipeline requirement. It has safety nets, cost controls, and 0 downtime mandates.
And the hive mind trap here is sometimes choosing an in-place deployment because people are, frankly, intimidated by the infrastructure overhead of blue-green. Or, more commonly, they completely mess up the chronological order of the app spec hooks when trying to delete those temporary files.
Yeah, the timeline gets people every time.
Let's break down the logic. The requirement states a new fleet of instances must be launched automatically.
That phrase immediately disqualifies any architectural options suggesting an in-place deployment. In-place, by definition, updates existing instances. Blue-green, by definition, launches a new fleet. So we know we're operating in a blue-green paradigm.
That narrows the field. Next requirement, traffic must be rerouted to half the new instances at a time.
This maps directly to the code deploy deployment configuration called code deploy default half at time. If you choose elitants, you shift 100% of the traffic instantly.
Right, which is scary.
Very. If the new code has a fatal memory leak, you cause a total global outage. Half A time provides a canary-like safety net. It shifts 50%, monitors health, and if it fails, the other 50% on the old fleet are still serving users.
Okay, here's the trickiest part, and where the forums just dissolve into arguments. Before routing traffic to the new fleet, temporary files must be deleted.
Yes.
I look at the remaining viable options. One suggests using the before block traffic app spec lifecycle hook to run the deletion script. Another suggests using the before allow traffic hook. Both are valid blue-green hooks, Both sound highly plausible. I'm blocking traffic, I'm allowing traffic. How do you logically deduce which one is correct?
This requires visualizing the exact chronological timeline of a server's lifecycle during a blue-green traffic shift. It is a very specific sequence of events, choreographed by code deploy and the application load balancer.
Walk me through it.
Let's walk through the timeline. First, the new EC2 instances, the green fleet, are provisioned by auto-scaling. Then, the standard code deploy installation hooks run on these new instances. Before install, install, after install.
Okay.
At this point, the new application code is physically sitting on the disk, but these new instances are completely isolated. They are not registered with the load balancer.
They're essentially invisible to the public internet.
Right. Then, code deploy runs the allow test traffic and after allow test traffic hooks if you have internal test listeners configured.
Got it.
Then comes the critical phase, shifting the actual production traffic from the old blue fleet to the new green fleet. The sequence of hooks during this traffic shift is paramount.
I'm listening.
The very first thing that happens on the new instances is the before allow traffic hook. After that hook completes successfully, code deploy reaches out to the application load balancer and registers the new green instances with the target group. Once registered, the ALB starts sending live user traffic to them. Finally, the after allow traffic hook runs. Okay, the light bulb just went on. The registration with the target group is the physical mechanism that allows traffic.
Exactly.
So if the business requirement explicitly states the temporary files must be deleted before routing traffic to the new fleet, you have to use a hook that fires right before that ALB target group registration occurs.
Yes. Before allow traffic runs on the new instances just before they are registered. If you use this hook to run a bash script that deletes temporary compilation files, you mathematically guarantee the files are gone before a single user HTTP request hits that specific server.
Right. Now look at the incorrect suggestion. Before block traffic, let's analyze where that runs.
Oh, this is important. Before block traffic runs on the original old blue instances right before they are deregistered from the load balancer.
Oh.
You do not want to run cleanup scripts on the old instances that you're about to destroy anyway. You want to clean up the new instances before they go live. That is a phenomenal breakdown.
Yeah.
You can't just guess based on the words allow and block.
No.
You have to know which fleet the hook executes on. Before allow traffic runs on the new fleet. Before block traffic runs on the old fleet.
Exactly.
So the optimal architecture is an application load balancer, a blue-green deployment group, the half-8 time configuration, and the before allow traffic hook in the app spec file to execute the cleanup script.
Spot on.
Let's look at one more CI/CD scenario before we move on. This one is less about the instances and more about the pipeline architecture itself. I call this decoupling the monolith pipeline.
Let's hear it.
The scenario is a company migrating a legacy web application to AWS. The code base is structured as a monorepo. Both the front-end code, which is a React application, and the back-end code, which is a complex Java application, are sitting right next to each other in a single GitHub repository.
Pretty common setup.
The engineering team needs to design a deployment architecture. Honestly, if I have one GitHub repository, my instinct is to build one giant AWS CodePipeline. The code lives together, it should deploy together. I'd configure a pipeline that pulls the source, builds the React app, builds the Java app, and deploys them both at the same time. It sounds easier to manage. Why is that considered an architectural anti-pattern?
What's fascinating here is that you are letting the physical storage location of the source code, the Git repository, dictate the infrastructure deployment architecture.
Oh, interesting way to put it.
This directly violates the core philosophy of microservices and agile delivery, which is independent deployability.
Explain the blast radius of that. Why do I care if they deploy together if it works?
Think about the day-to-day operations of your development teams. Imagine your front-end team notices a glaring typo in a CSS file on the homepage. They fix the typo and push the commit to GitHub.
Okay, simple fix.
If you have a single coupled pipeline, pushing that minor CSS fix triggers the entire monolithic process. The pipeline will pull the code, rebuild the front end, but it will also rebuild the entire backend Java application, run all the backend unit tests, and perform a rolling blue-green deployment of the backend EC2 instances just to update a style sheet on the front end.
Oh, wow. That's incredibly inefficient from a compute cost perspective, but it's also incredibly risky. You could accidentally introduce a massive back-end database outage while trying to fix a spelling mistake on the UI.
Yes.
The blast radius of a front-end deployment now encompasses the back-end.
Precisely. Deployment coupling creates artificial bottlenecks and unnecessary risk. The front end and back end have completely different build processes, different scaling characteristics, and entirely different deployment targets.
Right.
The back end Java application needs to compile binaries, run complex integration tests, and deploy to EC2 instances using CodeDeploy. The front end React application simply needs to compile static HTML, JS, and CSS using Node, and then sync those static assets to an Amazon S3 bucket behind CloudFront.
So how do we split the deployment if they share the exact same Git repository? Won't any commit trigger both pipelines?
Not if you architect it correctly using path-based filtering. The well-architected solution is to create two completely separate AWS CodePipeline pipelines, one dedicated to the front end, one dedicated to the back end. Both pipelines point to the exact same GitHub repository as their source action.
But how do we stop the CSS typo fix from triggering the Java deployment?
You configure the source action or the underlying event bridge trigger to filter based on file paths. You set a role that says, if a git commit only modifies files within the /frontend directory, only the frontend pipeline triggers. It uses AWS CodeBuild to compile the assets and deploys them directly to S3. The backend pipeline completely ignores the event.
That's brilliant.
Conversely, if a commit touches the /backend directory, the backend pipeline triggers, uses CodeBuild to compile the Java code, and uses CodeDeploy to push to the EC2 instances. You effectively decouple the release cycles while maintaining the developer convenience of a unified monorepo codebase.
That makes perfect sense. You isolate the blast radius based on the directory path. Never couple your release cycles just because you share a Git repo.
Exactly.
All right, we are shifting gears into our next major theme. Healing the fleet and architectural forensics.
My favorite topic.
Our CI/CD pipelines are perfect. We've pushed the code safely. It's out there in the wild. But the cloud is a hostile environment. Hardware degrades, memory leaks happen, processes crash. What happens when things go wrong in production?
Yes.
Exactly. How do we figure out why a server died before the auto-scaling group buries the evidence? Let's dive into a scenario I call catching logs before the grave.
Sounds ominous.
Here's the setup. An operations engineer is managing a fleet of 50 Amazon EC2 Linux servers. They are sitting comfortably in an auto-scaling group behind an application load balancer. Everything is humming along. But occasionally, seemingly at random, an application server process hangs. It fails the ALB HTTP health check. The load balancer marks the instance as unhealthy. It communicates that status to the auto-scaling group, and the ASG ruthlessly terminates the instance and launches a fresh replacement.
Standard auto-healing.
Right. The system is auto-healing, which is great, but the developer wants to perform a root cause analysis. They want to know why the process hung, they want to SSH into the box, and look at the raw application logs in the /var/log directory.
Sure, they need the evidence.
But by the time they get the PagerDuty alert, make a coffee, and open their terminal, the server is already terminated. It's dust. The EBS volume is deleted, the logs are gone forever.
Yeah, auto-scaling does not wait around for you to finish your coffee.
So the mandate is, how can log collection be fully automated before the instance is destroyed? I look at the community forums and people love Amazon CloudWatch alarms. The prevailing suggestion is to create a CloudWatch alarm that triggers an AWS Lambda function whenever an instance fails a health check. The Lambda function will jump in and grab the logs.
I see that answer all the time.
Let me work through why I think that's a terrible idea. If the instance is already failing health checks, the auto-scaling termination sequence has already begun. A CloudWatch metric has to aggregate, the alarm has to evaluate the state, trigger an SNS topic, which invokes a Lambda function, which has to spin up. But by the time all that happens, the instance is gone.
Yep.
You are racing a machine designed to be fast, and you will lose.
You are exactly right. You are racing against the orchestrator, and auto-scaling is ruthless by design. When it decides an instance is unhealthy, it issues the termination API call almost immediately.
So how do you beat it?
This raises a fascinating systems engineering question. How do you safely interrupt a managed service's core workflow? You cannot outrun it. You have to put it in a chokehold. You have to use the specific interception hooks provided by the service itself. In this case, we need to use auto-scaling lifecycle hooks.
So we explicitly tell the ASG to pause.
Yeah.
Explain how this freeze frame mechanic works.
A lifecycle hook allows you to intentionally pause an instance during its launch phase or, crucially for this scenario, its termination phase.
Okay.
When the ASG decides to terminate the unhealthy instance, the lifecycle hook intercepts that action. Instead of instantly shutting down the OS and deleting the volume, the instance transitions into a suspended state called terminating. Wait,
It's basically on death row, but it's been granted a temporary stay of execution.
that is exactly what it is. The instance is still powered on, its disk is still intact, the logs are still there, but it has been deregistered from the load balancer, so it's no longer serving user traffic. It is quarantined.
Wow. Now, how do we automate the forensic extraction?
When the instance enters this terminating wait state, auto-scaling emits a specific event to the default event bus. We can use Amazon Event Bridge to listen for that specific EC2 instance terminate lifecycle action event.
Okay, EventBridge catches the event almost instantly. Then what?
EventBridge uses that event to trigger an AWS Lambda function. This Lambda function is our automated forensic investigator. It doesn't try to SSH into the box. SSH requires managing keys and opening security groups, which is an anti-pattern.
Right, bad idea.
Instead, it executes an AWS Systems Manager, or SSM, run command script targeting that specific instance ID.
Because SSM agents are pre-installed on the instance, they maintain an outbound connection to the AWS control plane. The Lambda just tells SSM, hey, tell instance ID 1234 to run this bash script.
Yes, the SSM run command executes the bash script locally on the quarantined instance. The script zips up the application log directory, authenticates using the instance's IAM role, and pushes that tarball archive directly to a secure Amazon S3 bucket.
The evidence is secured and preserved indefinitely.
Exactly. Once the script finishes the S3 upload, it sends a success signal back to the Lambda function. The Lambda function then makes one final critical API call to the auto-scaling service, complete lifecycle action.
I see.
It essentially tells the auto-scaling group, I'm done with my investigation, you can drop the stay of execution and proceed with the termination. The instance is then fully terminated and the EBS volume is deleted.
It is the ultimate, elegant forensic loop. It guarantees you never lose logs due to auto-healing. It requires zero human intervention, and it doesn't leave broken servers running indefinitely.
Yep.
That is brilliant. You freeze the instance, extract its brain, and then let it die.
Pretty morbid, but very accurate.
Let's look at another auto-scaling friction point, but this time on the launch side, not the termination side. I call this the S3 data bottleneck.
Okay, let's hear it.
Imagine this scenario. We have an application running on EC2 instances in an ASG. It's a data processing application. When a new instance starts up, before it can serve a single HTTP request or process a job, it has to download a massive multi-gigabyte data set from an S3 bucket and load it into local memory or process it into a local SQLite database.
That's a heavy boot-up process.
It is. The data size is growing over time.
Yeah.
Now, when the ASG experiences a scale-out event due to high CPU, it takes several minutes for the new instance to download the data, process it, and signal that it's healthy.
Yikes.
This completely defeats the purpose of elastic scaling. If you need capacity now, getting it 10 minutes from now is an outage. We need to reduce this startup time drastically, but we need to do it cost-effectively.
Always cost-effectively.
The brute force answer, which I see constantly suggested, is just to increase the minimum instance count. If you need 10 instances during a spike, just run 10 instances 24/7 so you don't have to wait for them to boot.
That is the highest cost approach possible. If you just over-provision and run instances 24/7 to avoid startup latency, you are paying hourly compute charges for idle processors. It completely defeats the financial premise of elastic cloud computing.
So what is the elegant, cost-effective system architecture? We need the data there instantly, but we don't want to pay for the CPU while it waits.
The well-architected solution relies on a relatively newer feature called auto-scaling group warm pools.
Okay, we just used lifecycle hooks to pause termination. How does a warm pool fix a massive S3 download time?
Think of a warm pool as a pre-warmed staging area for instances, conceptually similar to what we discussed with Lambda provision concurrency, but applied to EC2.
Okay.
When you configure a warm pool, auto-scaling launches a predefined number of instances in the background, completely separate from your active traffic serving fleet. During the launch of these background instances, an autoscaling.ec2 instance launching lifecycle hook fires. Your instance boots up, runs its user data bootstrapping script, downloads the massive multi-gigabyte data payload from S3, crunches the data, and writes the final process state to the local EBS volume.
So it does all the heavy, time-consuming lifting up front.
Yes. Once it finishes the heavy lifting, the application signals the lifecycle hook that it's fully initialized. But instead of putting the instance into service to take user traffic, auto-scaling intercepts it and transitions the instance into a stopped state.
Wait, it actually shuts the server down via the hypervisor.
It stops the compute instance, yes. Yeah. But And this is the critical economic distinction, the EBS volume attached to that instance, which now contains all that downloaded, heavily processed data, remains attached and completely intact. Now, fast forward to 2:00 p.m. A sudden traffic spike occurs, and the active ASG needs to scale out immediately. Instead of launching a brand new empty instance and starting the 10-minute download process, the ASG reaches into the warm pool and simply issues a start command to one of those stocked instances.
And because it's just transitioning from stop to running, it doesn't need to install packages or download data. It only takes seconds to boot the operating system. And the massive S3 dataset is already sitting right there on the EBS volume, ready to be read into RAM.
Exactly. The minutes-long download and processing pipeline is completely bypassed during the critical scale-out event. And because the instances in the warm pool spend 99% of their time in a stop state, you do not pay the hourly EC2 compute charges while they sit there waiting.
You only pay for the disk.
You only pay pennies for the EBS storage. It is the absolute most cost-effective way to achieve near-instant scaling for architectures that require heavy stateful data initializations.
That is a masterclass in utilizing AWS primitives to separate compute costs from storage availability. Just brilliant.
It really is an elegant solution.
All right, one more forensic deep dive before we move to governance. This one is about the limits of observability. I call it the out-of-memory ghost.
Spooky theme today.
Right. Scenario. A DevOps engineer is monitoring a dashboard and notices a disturbing pattern. All the EC2 instances behind an application load balancer in an auto-scaling group are intermittently failing to respond to requests. They are failing the ALB health checks, being terminated, and being replaced.
Okay, we've seen this before.
The engineer digs in, pulls the logs using the forensic architecture we just discussed, and finds that the application process, let's say it's a Java virtual machine, has completely crashed. The system logs are full of or out-of-memory kill messages from the Linux kernel.
Ah, the classic memory leak.
The business requirement is to improve resilience against this memory leak, and critically, to enable monitoring and proactive notifications when memory starts getting dangerously full before the crash happens.
Makes sense.
If I look at the proposed solutions, some suggest just changing the auto-scaling configuration to aggressively replace instances the second they drop a packet.
No.
Auto-healing. If it fails, replace it faster.
Auto-healing is a necessary component of a resilient system, but in the context of a severe memory leak, it's only a superficial band-aid.
Right.
If you have a fundamentally leaky Java application, the new replacement instance will just boot up, fill up its RAM over the course of an hour, and crash too. You'll enter an infinite crash loop. You are just treating the symptom.
The core requirement here is observability. The engineer needs to know when memory is filling up so they can capture a heap dump and fix the code leak, not just constantly reboot dying servers.
Exactly.
So how do we get that visibility? AWS monitors all these instances, right? CloudWatch has dozens of metrics. Why can't I just go into the CloudWatch console, select the EC2 instance, and set an alarm on the memory utilization metric to page me at 85%?
Because that metric does not exist by default.
Wait, really?
Really. And understanding why it doesn't exist is a critical systems engineering concept related to virtualization. You have to understand the boundary between the AWS hypervisor, the Nitro system, or eggs, and the guest operating system running on your EC2 instance.
Okay, lay it on me.
The hypervisor provisions a physical block of RAM to your instance, say 16 gigabytes. From the hypervisor's perspective, it has handed over those 16 gigs, but the hypervisor cannot see inside the guest operating system's memory allocation table.
Interesting.
It doesn't know if that RAM is completely empty, if it's full of harmless cached files, or if it's completely exhausted by a leaky Java application.
Oh, so the hypervisor only sees the outside of the black box. It's like a landlord who rents you an apartment.
Okay, I like this.
The landlord knows you are using the apartment. They can see you walking in and out the front door, which is network traffic, and they can hear if you're playing loud music, which is CPU usage, but they have absolutely no idea if your bathtub is currently overflowing and ruining the floor.
That is a brilliant analogy. The landlord cannot look inside the apartment. Therefore, there is no default memory utilization metric in CloudWatch for EC2 instances because AWS physically cannot read it without violating the security boundary of your OS.
Wow.
If you want memory metrics, you have to push them from inside the apartment.
Which brings us to the architectural solution. We need an insight agent. We need to use the Amazon CloudWatch agent.
Yes. The well-architected solution is to install and configure the unified CloudWatch agent on your EC2 instances, usually baking it into the AMI or installing it via user data.
Right.
The agent runs as a daemon inside the Linux or Windows OS. It has local administrative rights. It reads the actual memory statistics from the kernel, packages that data, and pushes it outward as a custom metric to the CloudWatch API.
Once you have that internal data flowing to CloudWatch, you can finally set your alarm. You configure an alarm to trigger an SNS notification when the custom memory metric hits 85%. You get paged before the OM crash happens, giving you time to log in, capture a diagnostic heap dump of the JVM, and gracefully restart the application before the user ever experiences an error.
Perfect. It's about instrumenting the inside of the box, understanding the limits of the hypervisor, and moving from reactive auto-healing to proactive observability.
All right, let's shift into our final major theme of the deep dive. Automated governance and event-driven security.
This is where things get really massive.
They do. We've scaled our serverless apps. We've mastered complex blue-green deployments. We've frozen dying instances for forensics. We are operating at a high technical level. But if you're working at an enterprise scale, technical perfection isn't enough.
No, you need guardrails.
Exactly. How do you govern hundreds of AWS accounts, thousands of resources, and enforce strict security policies without becoming a massive bureaucratic bottleneck for your development teams? Let's look at an architectural scenario focused on enforcing IAM instance profiles.
Okay, shoot.
Scenario. A large company has hundreds of EC2 instances running across their environment. New instances are launched by automated pipelines every hour, and old ones are terminated. But there are also legacy instances that have been running untouched for weeks or months.
Pretty typical for a large org.
The central security team issues a new mandate. All running EC2 instances, without exception, must use an attached IAM instance profile. If an instance is discovered without one, it must immediately be assigned a default, heavily restricted profile with 0 permissions.
That's a strong mandate.
The DevOps engineer looks at the environment and realizes there are currently instances running without profiles. How do we build an architecture to ensure all existing and future instances comply with this mandate automatically?
I can already guess the trap here.
The Hivemind trap here is incredibly tempting because it uses modern event-driven tools. The forums suggest configuring an Amazon Event Bridge rule that reacts to AWS CloudTrail events.
Yep.
Specifically, they say to listen for the EC2 run instance's API call. When that API call happens, EventBridge triggers a Lambda function that inspects the request, and if there's no IAM profile, it attaches the default one.
Sounds super slick, right?
I mean, logically, it makes sense, catch them in the act, but let me push back on the timeline here. If we rely on EventBridge listening to the run instance's API call, we're only catching new servers being created right now.
Exactly.
What about the 100 legacy instances that were launched last week that are currently sitting there happily running without a profile? The run instances event for those servers happened days ago. EventBridge won't see them.
You've hit the exact flaw in that architecture. Event-driven enforcement using CloudTrail and EventBridge is fantastic for point-in-time reactive actions. A user did X, so I will immediately do Y. But it is entirely blind to the existing historical state of the environment. EventBridge does not look backward. Furthermore, if your Lambda script happens to crash or time out during the split second that the run instance's event occurs, that new instance slips through the net and remains non-compliant forever because the event is gone.
It only looks forward and it has no memory. So what is the AWS service designed to actually look at the overall holistic state of the environment?
For state-based governance, you must use AWS config. The well-architected solution here is to configure an AWS config managed rule, specifically the EC2 instance profile attached rule.
Break down why AWS config is superior for this specific mandate.
AWS config acts as a continuous inventory and configuration history engine. When you enable it, it performs an initial baseline scan of the current state of all your supported resources. It creates configuration items.
Okay.
The managed rule EC2 instance profile attached explicitly checks the configuration state of every single EC2 instance in the account, past, present, and future. If it scans the environment and finds an instance from last week without a profile, it flags it as non-compliant. If someone launches a new instance tomorrow without a profile, config detects the configuration change, evaluates it against the rule, and flags it as non-compliant.
Okay, so it finds the violators perfectly,
Yeah.
but the mandate said we have to automatically fix them, not just flag them.
Yes, and this is where AWS config outshines custom Lambda scripts. AWS Config has native deep integration with AWS Systems Manager, or SSM, automation runbooks for automatic remediation.
Yeah.
You configure the config rule with an automatic remediation action. As soon as a resource is flagged as non-compliant, config natively triggers a predefined SSM runbook. That runbook executes the necessary API calls to assume a role, find the specific instance ID, and attach the default zero-permission IAM profile to it.
It's incredibly powerful.
It is continuous state-based governance. It ensures compliance regardless of when the resource was created, how it was created, or if a previous remediation attempt failed. It continuously forces the environment back into the desired state.
That is the crucial difference between event-driven reactions and state-based governance. One is a tripwire, the other is a continuous patrol.
A continuous patrol, I love that.
Let's scale that governance concept up to an even higher level, an entire organization. I call this the approved AMI enforcement.
Okay, moving up the ladder.
Scenario. A central DevOps team manages dozens of different AWS accounts within a master AWS organization. They need a solution to ensure that all EC2 instances launched anywhere in the company use specific, hardened, approved AMIs managed by the DevOps team.
Okay.
Just like the last scenario, it must automatically remediate non-compliant instances by stopping them. But here is the critical organizational twist. Individual account administrators, the lead developers who own those member accounts, must not be able to bypass, modify, or remove this restriction.
Ooh, the classic political and technical challenge.
Right. If a developer has administrator access to their specific AWS account, they can do whatever they want, right? If I just deploy an AWS config rule using CloudFormation stack sets into their account, the local admin can simply log in, navigate to the config console, and delete the rule or delete the remediation action and go back to launching unapproved images. How do we strip that power away and make it immutable from the top down?
You've identified the exact limitation of standard account-level config rules in a multi-account environment. If the local user is an admin, they can undo your guardrails.
How do we stop them?
To solve this, we elevate the architecture to the organizational level using AWS config conformance packs deployed via AWS organizations.
What makes a conformance pack deployed via organizations fundamentally different from just pushing a regular config rule via a script?
It comes down to immutable permissions and service control policies, or SCPs, operating under the hood. When you deploy a conformance pack from the organization's management account or a delegated administrator account down into the member accounts, the resources created by that pack are treated entirely differently.
Different how?
The config rules, the evaluation logic, and the remediation associations created by the pack are completely immutable within the member accounts.
Immutable meaning they literally cannot be changed by the local user.
Correct. Even if a rogue developer has the administrator access managed policy attached to their IAM user in that member account, the AWS control plane will deny any attempt to modify or delete the rules deployed by that organization-level conformance pack.
That's crazy.
They will get an access denied error. They are completely locked out of the governance mechanisms.
Wow. So the central team deploys the pack. It enforces the approved AMIS by I rule. It natively triggers the AWS StopBack2 instance SSM runbook to kill the non-compliant server, and the local admin can do absolutely nothing to stop it, pause it, or delete it. That is ironclad, inescapable governance.
It's absolutely necessary in highly regulated environments like finance or healthcare. You must have technical mechanisms that cannot be subverted by local, well-meaning, but perhaps non-compliant actions to speed up a deployment. Conformance packs provide that top-down, unalterable authority.
Let's look at one final scenario to tie our operations together. This is about situational awareness, correlating AWS health events.
Okay, good topic.
Scenario. A company wants to proactively monitor underlying AWS platform. Issues things completely out of their control, like an availability zone, power degradation, degraded network hardware, or an underlying API failure. But they don't just want an email alert. They want to correlate those AWS platform health events directly with their own application performance metrics, setting up automated correlated alerts.
This is next-level maturity right here.
Usually, AWS health issues are just a vague notification. You get an email saying, hey, an EC2 instance underlying your host had a hardware failure. It's informative, but it's not operational data. How do we take a vague platform alert and overlay it onto our own specific application dashboards?
You have to bridge the gap between the AWS platform's control plane events and your application's data plane metrics. You have to turn an event into a number.
Walk me through the exact data flow of how an email becomes a metric.
AWS Health natively emits operational events to the Amazon EventBridge default bus. EventBridge is the central nervous system for all AWS activity. You create an EventBridge rule that says, capture all events where the source is oz.health and route those event payloads directly into a specific Amazon CloudWatch logs log group.
Okay, so now instead of emails, we have a searchable, centralized log of every single platform issue that has ever affected our account.
Right, it's now data. Next, you create a CloudWatch metric filter on that specific log group. The filter is configured to look for specific error keywords in the JSON payload, like OSS2 instanced or drive error or degraded eyes.
Okay.
Every single time the filter sees that string pattern in the logs, it increments a custom CloudWatch metric. Let's call that custom metric AW hardware failures.
Okay, I follow the transformation. We turned an event payload into a numerical metric on a graph. So now I have a graph on my dashboard that spikes from 0 to 1 when AWS hardware fails. How does that correlate to my application?
Your application is already heavily instrumented. You already have custom metrics flowing for things like checkout latency, 500 errors, or database timeouts. Now you can use a feature called CloudWatch Metric Math. You can create a composite alarm or simply build a dashboard that visually overlays the AWS hardware failures platform metric directly on top of your checkout latency application metric.
Oh, that is cool.
Think about the operational value of this. When your pager goes off at 3:00 a.m. because your checkout latency just spiked 400%, your first instinct is usually, who deployed bad code? You spend 20 minutes rolling back deployments, checking database locks, and waking up developers.
That's always a fire drill.
But with this correlated dashboard, you look at the graph and you see a massive spike in checkout latency. But right underneath it, at the exact same minute, you see a corresponding spike in the AWS hardware failures metric.
You instantly know it's a platform hardware issue, not a bad code deployment.
Yeah.
You don't roll back the code. You don't wake up the front-end team. You just terminate the instance and let the ASG replace it on healthy hardware. It drastically reduces your mean time to resolution by eliminating all the investigative guesswork.
Exactly. You are fusing the AWS control plane context with your application's data plane context. It is the pinnacle of operational awareness.
We have covered massive, dense architectural ground today.
We really did.
We navigated the physical traps of database connection starvation by putting an RDS proxy in front of Aurora, intelligently multiplexing connections to shield the database from the brutal horizontal scaling of Lambda.
Yep, saving the database is one proxy at a time.
We solved the DynamoDB cold start latency by separating the concept of data caching with DAX from the necessity of compute pre-warming, utilizing dynamic provision concurrency schedules with application auto-scaling to save money at night.
A very elegant solution.
We mastered the dark arts of CI/CD and code deploy. We realized that simple in-place deployments can get completely wrecked by scaling out midway through a deployment, creating phantom instances with old code.
The moving train.
Right. We learned the exact chronological sequence of app-spec hooks, proving that you must use before allow traffic to delete compilation files before a blue-green canary registers with the load balancer target group.
Crucial timing.
We became forensic investigators, utilizing auto-scaling lifecycle hooks to freeze dying instances in a terminating. Wait state just long enough for EventBridge, Lambda, and SSM run command to extract the logs to S3 before the instance turns to dust.
Freeze it, extract it, delete it.
We used ASG warm pools to bypass massive multi-minute S3 data download times, paying only for EBS storage while keeping compute instances in a stop state. And we installed unified CloudWatch agents to find out-of-memory ghosts, proving that the AWS hypervisor cannot see inside the guest OS black box.
The landlord doesn't know about the overflowing bathtub.
Exactly. And finally, we locked down the enterprise. We used AWS config for continuous state-based enforcement of IAM profiles. We utilized organization-level conformance packs for immutable top-down AMI governance that local admins cannot bypass. And we piped AWS health events through EventBridge to visually correlate platform data center failures with our own application latency.
Wow. If you take away anything from this deep dive, let it be this operating at a high level of cloud architecture isn't about memorizing multiple choice options, and it isn't about knowing what an acronym stands for.
No.
It's about internalizing how these distributed systems interact mechanically at a microscopic level. It's about understanding that every single architectural choice, like choosing provision concurrency over DAX, or an AWS config rule over an event bridge trigger, or a blue-green deployment over an in-place update, has a distinct mechanical purpose based entirely on how the underlying physics of the cloud operate.
You have to know why the X-ray machine is broken and understand the physics of the radiation, not just point out that the picture is blurry.
Beautifully said.
I want to leave you with a final provocative thought, building on the advanced automation concepts we've touched on today. We spent an hour discussing using CloudWatch, EventBridge, AWS Config, and SSM to automatically remediate issues. But all of these architectures are deterministic. They rely on human-written rules. If X happens, run script Y.
Right, very rigid.
But as we see tools integrating machine learning into the operational mix, they are starting to predict anomalies based on statistical deviations before they ever crash the system. So, ponder this. As predictive anomaly detection gets better, how long until our CI/CD pipelines and auto-scaling groups don't just rigidly follow our hard-coded app spec files and scaling policies?
Oh, that's an interesting thought.
How long until the infrastructure actively rewrites its own scaling thresholds, modifies its own deployment rollout speeds, and alters its own auto-scaling configurations in real time, autonomously adapting to predicted traffic shapes without any human intervention or approval?
Self-rating architectures.
Exactly. Are we just building static automated systems today, or are we laying the groundwork for digital immune systems that will eventually manage, scale, and heal themselves entirely on their own? Something to ponder before you merge your next massive infrastructure pull request. Keep digging deep into the cloud. We'll see you next time.